Now we're going to talk about kinetic energy. This is part 2 of the notes. Part 2 of the energy notes. Kinetic energy of a moving object is equal to the work required to bring it to its speed from rest, or the work the object can do while being brought to rest. These kinetic means moving. Oops. Kinetic means moving, so it's going to be stuff that is moving. If an object is moving, then it's capable of doing work. It has energy of motion, or kinetic energy. The kinetic energy of an object depends on the mass of the object as well as its speed. It is equal to half the mass multiplied by the square of the speed. Kinetic energy equals 1/2 times the mass times the velocity of the object, or the speed, squared. Just the speed is squared. None of the other stuff is squared. When you throw a ball, you do work on it to give it speed as it leaves your hand. The moving ball can then hit something and push it, doing work on something else. So this is called the work energy theorem, because basically kinetic energy we said was 1/2 mv squared, and then we said work was force times distance. Well, if you apply a force and move something a distance, is it moving? Yes. So and if it's moving, it has kinetic energy. So you can set work equal to it, because remember, work is measured in joules and energy is measured in joules. Note that the speed is squared, so if the speed of an object is doubled, the kinetic energy is quadrupled. Anytime you square something, it's going to quadruple it on the other side. It takes 4 times the work to double the speed. An object moving twice as fast takes 4 times as much work to stop. How are work and kinetic energy of a moving object related? I just explained that. Remember, force times distance, our work, equals 1/2 mv squared. So the work energy theorem states that whenever work is done, energy changes. Important note. Important note. To increase the kinetic energy of an object, work must be done on the object. If an object is moving, work is required to bring it to rest. The change in kinetic energy is equal to the net work done. The work energy theorem describes the relationship between work and energy. That's what we started talking about in the last few slides. We abbreviate change with the delta symbol. So if we say work equals the change in kinetic energy, that just means change. That little triangle. So work equals the change in kinetic energy. The work in this equation is the net work. That is the work based on the net force. If there is no change in the object's kinetic energy, then no net work was done on it. Push against a box on the floor. If it doesn't slide, then you are not doing work on the box. On a very slippery floor, there is no friction at all. The work on your push times the distance of your push appears as kinetic energy of the box. If there is some friction, it is the net force of your push minus the frictional force that is multiplied by the distance to give the gain in kinetic energy. If the box moves at a constant speed, you are pushing just hard enough to overcome friction. The net force and the net work are 0, and according to the work energy theorem, the kinetic energy equals 0. The kinetic energy doesn't change. The work energy theorem applies to decreasing speed as well. The more kinetic energy something has, the more work is required to stop it. Twice as much kinetic energy means twice as much work. Yay. Due to friction, energy is transferred both into the floor and into the tire when the bicycle skids to a stop. An infrared camera reveals the heated tire on the track. You kind of got cut off down here. There you go. As he skids to a stop, you see heat. Heat is another form of energy. When a car brakes, the work is the frictional force applied by the brakes multiplied by the distance over which the force acts. A car moves at twice the speed of another has 4 times as much kinetic energy, and while required 4 times as much work to stop. The frictional force is nearly the same for both cars, so the faster one takes 4 times as much distance to stop. Kinetic energy depends on the speed squared. Remember, we're going to talk about this and we're going to work problems in class about kinetic energy. Alright, typical stopping distances for cars equipped with anti-lock brakes travel at various speeds. The work done to stop the car is the friction force times the distance. Here are some more. At 45 kilometers per hour it takes 10 meters, at 90 it takes 40. See, we doubled the speed and we got 4 times the distance. Double the speed, 4 times the distance. Double the speed, 4 times the distance. Kinetic energy often appears hidden in different forms of energy, such as heat, sound, light, and electricity. Random molecular motion is sensed as heat. Sound consists of molecules vibrating in rhythmic patterns. Light energy originates in the motion of electrons within atoms. Electrons in motion make electric currents. These are all different types of kinetic energy. We're not going to get into all of them right now, but we will kind of discuss them later on in the year. Alright, a friend says if you do 100 joules of work on a moving cart, the cart will gain 100 joules of kinetic energy. Another friend says this depends on whether or not there is friction. What is your opinion on this statement? Careful, although you do 100 joules of work on the cart, this may not mean that the cart gains 100 joules of kinetic energy. How much kinetic energy the cart gains depends on the net work done on it. So there could be some frictional force, so you have to subtract that away. When the brakes of a car are locked, the car skids to a stop. How much farther will the car skid if it's moving 3 times as fast? So it'll go 9 times farther. The car has 9 times as much kinetic energy when it travels 3 times as fast. What is the work energy theorem? Remember we said the kinetic energy and the work are equal to one another. Alright, law of conservation of energy. This is a big one. The law of conservation of energy states that the energy cannot be created or destroyed. It can only transfer between states. The total amount of energy never changes. This is the key concept to maybe all of physics. All of physics, it all breaks down into this one law, that you're not losing or you're not destroying anything. It's just transferring between states. More important than knowing what energy is understanding how it behaves, how it transforms. We can understand nearly every process that occurs in nature if we analyze it in the terms of transformation of energy from one form to another. Potential energy will become the kinetic energy of the arrow. Pull it back, you have potential energy holding the arrow in place. Once you let go, you've transferred that potential energy into kinetic energy. As you draw the arrow in back the arrow with a bow, you do work stretching the bow. The bow has the potential energy. When released, the arrow has kinetic energy equal to this potential energy. It delivers this energy to its target. The small distance the arrow moves multiplied by the average force of impact doesn't quite match the kinetic energy of the target. However, the arrow and the target are a bit warmer by the energy difference. Energy changes from one form to another without net loss or gain. What they're saying here is whenever you pull the bow back, let's say that you had 100 joules of energy, of potential energy. You let go and there's 100 joules of kinetic energy. It hits the target, but there's only 98 joules of energy when it hits the target. Well, what it's saying is when it hits the target, you're going to have a little bit of a heat as it rubs through the target. You're going to have a little bit of energy transfer into heat as it hits the target. That's where the other 2 joules went. The study of the forms of energy and the transformations from one form into another is the law of conservation of energy, or any system in its entirety. As simple as swinging pendulum or as complex as the exploding galaxy, there is one quantity that does not change, which is energy. Energy may change forms, but the total energy stays the same. Key terms. Part of the potential energy of the world spring changes into kinetic energy. The remaining PE goes into heating the machinery and the surroundings due to friction. No energy is lost. So you have this little, it starts with 10 joules, moves forward with 8 joules, but you have a little bit of friction here on the floor working on it, which you lose 2 joules to heat. Everywhere along the path of a pendulum, as it swings back and forth, the sum of potential energy and kinetic energy is the same because of the work done against friction. This energy will eventually be transferred into heat. So if I'm holding it here, this is my line, it's just sitting still, it's just potential energy. As it starts to swing down, it has both potential energy and kinetic energy. It's moving, so it has kinetic, but it's not all the way at its 0 point, so it has potential still. Down here at the bottom, it has all kinetic energy because it's moving, but it can't go any lower, so there's no potential energy left. And then when you get back up here to this point on this side, it's basically the same as where you started here. When the woman leaps from the burning building, the sum of her potential energy and kinetic energy remain constant at each successive moment. Up here, she's got all 10,000 joules of potential energy and no kinetic. Here, she's got 7,500 joules of potential and 25 of kinetic. Halfway down, it split 50-50. And then you see it flips from where it was right up here. And then at the bottom, as she's hitting, she's all kinetic and no potential. Each atom that makes up matter is a concentrated bundle of energy. When the nuclei of atoms rearrange themselves, enormous amounts of energy can be released. The sun shines because of its nuclear energy is transformed into radiant energy. In nuclear reactions, nuclear energy is transformed into heat. Enormous compression due to gravity in the deep, hot interior of the sun causes hydrogen nuclei to fuse and become helium nuclei. This high-temperature welding of atomic nuclei is called thermonuclear fusion. This process releases radiant energy, some of which reaches Earth. Part of this energy falls on the planet, and some of the plants later become coal. Another part supports life in the food chain that begins with microscopic marine animals and plants and later gets stored in oil. Part of the sun's energy is used to evaporate water from the ocean. Some water returns to Earth as rain that is trapped behind a dam. The generating plant transforms the energy of falling water into electrical energy. Electrical energy travels through the wires to becomes which is used for lighting, heating, cooking, and operating electrical brushes. What does the law of conservation of energy state? It states that energy is never created or destroyed, it will just transfer between states.